Hello everyone, myself Shubhain Mishra. I'm application engineer in Arc Info Solutions. The Arc Info Solution is basically a service provider for Ansys. Basically, when we are dealing with the electronics field, what happens there are some limited markets in the electronics. Plus, electronics is basically used in all markets. Wherever industry is this, electronics, there is electronics. When we are before going to the electronics part, first I would like to tell you about what is Ansys and how we are different from our our competitors. So basically, Ansys is a simulation tool. What's so question arises? What's the need of simulations? So basically, when we want to study the characteristics of some materials, like I want to study the S parameters and other things. So for that purpose, we will what we will do is we will replicate a a copy of that material, and we will analyze that material in the tool, and we will let know like what type of problems you are facing and what are some challenges you can resolve before the designing process. So there are the various companies who are using simulation softwares, but we are different from others. We are basically the two times the size of our nearest competitors. Whatever our nearest competitors, we are basically the two times the size. We are number one in simulations. When we deal with the simulation part, like there are other our competitors, what they do is they focus on many things. But what we do is we basically focus on the simulation part. Like when our we focus on the one thing, we can achieve more accurate and our more accurate results. We have some 32 billion market capitalizations. When we are dealing with the customer satisfaction, what basic requirement is like how customers are satisfied and other things. So our overall customer satisfaction globally is 89%. When you have to deliver some for the customer satisfaction, what we need some we need manpower. So what we have is we have 4,800 employees globally. There are 85 ANSYS offices and 150 channel partners globally. So then when we are doing some when we are solving some problem, so we can't solve whole problem with just one physics. So what we need is multi-physics domain. So going to the multi-physics, we have these are the various our tools which can solve any type of problem. We have a Granta MI. Granta MI is basically for material. Like when we are designing something, so selection of material is very important. It can reduce the pricing and performance also. So for that we have Granta MI. We have Connect tool. Connect tool is basically for optimization. I'm some for electronics field. Like I'm some designing some antenna. Okay. So after designing, what I need to do is we want to optimize. We want to change the parameters, but we don't need to design the whole. We don't need to go to the first step of the designing. So what we will do is we will just change the parameter through OptiSlang. Here you can see that there is an optimization tool OptiSlang. So we have embedded softwares when we want to do the simulations in the embedded field. So we have skate display, skate vision. For safety purpose, we have Medini software here, digital Medini we have for safety analysis. And when we move to the AV simulations, when we want to do some AV simulations, so for that we have headlamp and sensors. When we are going to the mission engineering part, for mission engineering we have STK, ODTK. We have digital twin for I'm designing some material. So what happens we want to analyze the performance. Like after some time, what will be the performance? So what we will do is we will replicate a digital copy of that design, and we will implement in the digital twin, and we will analyze the performance after 5 to 6 years. how performance will change and what type of problems we can face. Like for 3D designing, we have discovery. Phase three, just there you can see that day three, structure, fluid, and electronics. These are our basic physics requirements. Like when we are going to the structure field, like I want to analyze some turbo machines and other things. So we want to analyze some fluid type of things. So we have fluid, and for structures we have mechanical. And basically, what we are doing, we will focus on the electronics part. So in electronics itself, electronics is divided into two parts. First one is LF and other things is HF. So here you can see that the HFSS, SI wave, ISPAC, Q3D, NUHertz, EMA3D cable, EMA3D charge. These are the parts of the HF and Maxwell, MotorCAD, NUHertz, EMA3D cable, EMA3D charge, and ISPAC. These are the part of the LF. Like there are other tools also like semiconductors when we want to analyze some semiconductors things. So we have Red Hawk. When we move to the optics and VR fields, we have Spears. And when we want to like some photonics part, we want to go to the photonics part, we have a tool called numerical. And these are the various tools where you can use in your applications. And these are the various our customers. Like we have Lufthansa, Cat, Samsung, Nestle. There are various more customers, but I'm just letting you know the some of them. These are our academic customers and Ansys partners. Like IITs are also using NITs and NITTR. These are the various our academic customers here. So, like when we are doing some EV simulations and other things, so what we need is like in EV simulations, what happens? There are various things implemented in one system. Like we have a motor, we have antenna, we have sensors, and other things. To analyze whole thing, what we will do is we will just couple those things in the our tool, and we will analyze that. So in HF itself, I already told you about that there are various tools in HF for that for our analysis. So first one is HFSS. As you must be already known about the HFSS. HFSS is basically for like I want to design some geometry. I want to some design some entire geometry. For that we have HFSS tool. It basically focus on like I want to design some antenna, I want to place antenna over something, and I want to do the VR simulations and other things. So for that purpose, we have HFSS. HFSS basically use the various solvers like FEM, IE, integral equation solver, hybrid solvers. So next tool is SI wave. SI wave is basically for like I want. It is basically dedicated to the PCB part. Like I want to analyze some, I want to do signal integrity test or power integrity test. So for that purpose, we have a tool called SI wave. We have a ice pack. Like as we already know that temperature can affect our whole design. I'm designing something, and our whole process is accurate and other things, but temperature can affect that design. So for that purpose, we have ice pack tool. And when we are going to do some designing part and other analysis part, so what we know is we need to extract the RLGC parameters. To extract those RLGC parameters, we have a tool called QCD extractor. Like I already told you that there are in a car, like even 3D cable, I will just explain you with one example. Like there is a car built. Okay, so there's a cable installed. To analyze that cable, like that cable is how interpaired with other our materials like antenna and other things. So for that purpose, we have a tool called EMA 3D cable. EMA 3D charge is basically for like I'm designing something and I want to analyze some charging and discharging phenomena. To analyze those charging and discharging phenomena, we have EMA 3D charge. And NOH filter solution is like in the previous, what happens like when we are designing a filter. Okay, so what we need to go through the whole process, like analyzing the parameters and other things. So overcome that, what we have inbuilt is like all you have to do is like just provide some values and filter will be automatically designed. Like I will just say that it is a template based tool. Like there is a template and all you have to do is just enter the values and whole filter will be designed itself and it will be imported to the HFSS for analysis part. So in this, if you have any query, you can ask till now. Like if you want to explore some other tools, we will in future we can connect our other technical experts. Like in Ansys, what happens is like for every physics, we have a specified technical specialist. Like for like when we are like in the previous slides, like when we are going to the materials or we want to do some mechanical analysis. So for that each phase, like I've already explained to that, we have a special technical expert who is going to help you in whatever type of problem you are facing. So till now, if you have any query, you can ask. You can drop in the chat box also. If you have any query, you can send in the chat box.
Hello,
Yes.
sir. I want to ask if I want to simulate an antenna on an airborne platform, so just like
Okay.
aeroplane. So on
Okay.
HFSS, what should we do? How should we do that?
So like you want to place an antenna over something. Okay. So what you
Yeah.
need is to design the antenna and create a 3D component. Like creating 3D component, you already know about that or not?
Yes, yes,
How
I
to
know it.
create? Yeah, yeah. So create that 3D component and import that. Like you want to import that design on the helicopter, aeroplane, helicopter, anywhere. So import the design of that helicopter or aeroplane, whatever the design is. Like I want to place antenna over some PCB
That
and something.
aeroplane thing is not in HFSS, so that we can directly fetch it from the software and
Yeah,
place it
we
on
have
the.
we have a components library where you can find the tons of there are various already inbuilt 3D components there, so you can import from there also. Okay, so
So
Rahul,
one question from my side. Basically, you
okay,
mentioned ice pack is CFD solver, right?
yeah, yeah,
So do you think CFD guys can work on ice pack simulation
yeah.
as well? Yeah, okay,
Yes, you can. Basically, what happens is like it uses the FEM solver, but
correct.
it is a part of electronics tool. So you can, if you
Okay,
have little bit knowledge about in the next slides, I will go through that like what we are using
sure, sure.
automated adaptive mapping techniques. So you
Okay,
can
thank
do
you.
that in.
Yes, sure, thank you.
So these were the basically the electronics tools. So now we'll move to the part. Like as already told you that electronics is basically divided into two parts, the LF part and the HF part. Low frequency part is basically dedicated to the electric machines, motor cats and all. And the high frequency is basically dedicated to the where like I want to do some EMI simulations or I want to do some electrifications or electronic reliability like signal integrity, power integrity, thermal. Like I want to go to the antenna designing part and other thing. So we will move to the HF part. So before going in deep explaining the other tools our electronics HF tools, I'll go to the core of electronics. Like what are the core four for the our electronics tools. So first one is HFSS. So as I already told you that HFSS is basically dedicated when we are designing something, what happens is our first step is to create the geometry or import the geometry. Like if you have already created the geometry, you will import that and validate like if there is any error or any type of problems you are facing, like you are giving the codes excitement, like you are giving the perfect porting or you are giving the boundary conditions to analyze all things. These things will be done in the HFSS. The next one is when we move to the SI wave. SI wave is basically like I want to do some single integrity. In the next slide, I will explain you what is single integrity and power integrity things. So I want like I have a perfect. I want to just dedicate work on the PCB part. So in PCB, like from the EMI EMC, I want to do the EMI EMC or DDR analysis or anything. You can do that in the SI wave. The third one is basically for iStack. As I already told you that iStack is basically for some temperature is changing or other things. So for that we have iStack. And the last one is Maxwell. Maxwell is basically low frequency tool. It is basically dedicated for the electric machine. Like I want to design some electric machine or I want to work on some like I already told you the electrification part. So I want to analyze some transformers, actuators, or other electrothermal components. Like I want to work on the motors. So for that purpose, we have Maxwell. So these are our HF, like electronics core cores, which will basically deals with the like other tools like you are talking about the Q3D and EMA 3D cable. Another, these are all coupled with these tools. They will help these tools to work and find the problem, what type of solutions we need. So these are the various applications we can use our tools. Like for I want to do some antenna design and other things. So these will come in the wireless communication part, which will done from the HFSS. Like I want to work on the some smart devices. Like we are dealing with the RF interference. We can do that in the Ansys emit tool. Emit tool is basically for like when we are dealing with some RF. Like I want to analyze some in the defense. Like I want to analyze how much like interference between the other tools and other things are done. Then like I want to predict the like there is a enemy. So I want to extract the location of that enemy. For that other phase, we have Ansys emit tools for like yeah, for the SAR analysis and other things. These things will be done in the SI way. Like we have some signal integrity, power integrity, and EMI EMC analysis testing. So these things will be done in the SI way. The EMA 3D cable and EMA 3D charts, like I want to extract some parasitic RLGC extractions. We can do that from Q3D. Like there is some passive circuit analysis. Basically, what happens is one more most important thing when we are dealing with the multi-physics part is co-simulations. Like how co-simulation is basically how we link one tool from to other. Like I'm designing some antenna in the HFSS and I want to do the circuit analysis of that antenna. So what we will do is we will design that antenna in the HFSS. We will design that antenna in the HFSS and we will put simulate that to the circuit and we will do the circuit analysis in the ANSYS circuit. We have ANSYS NU words for like I want to generate some filter design or other things. So these are the basically our HF tools. Now we will move to the like LF tools. Like I want to do some advanced field analysis or efficiency map or torque speed analysis. This can be done from the MotorCAD and Maxwell. Like I want to do some system and power circuit design, other things we can do it from the Simplorer. Simplorer is basically when we are in the HF tools, like there is a circuit tool. So in the LF we have Simplorer. Like I want to do some structure and thermal analysis. So for that we have ice pack. So in the red part, you can see that in the red part, the tools these are the HF tools, and in the yellow part, you can see these are the LF tools. And in between Q3D circuit and UHz ice pack, these are of the both LF and HF. So this is basically how our workflow for like how we will design and how we will analyze our results. So first step is we will create a geometry. Like I got some problem. So first step will be how to create geometry, and those things will be done in the HFSS. Meshing, we don't need to worry about that because we are already using automatic adaptive meshing techniques, which will resolve your whole geometry and we will mesh that. So what happens is like we don't simulate the geometry, we simulate the mesh. Okay, so in this automatic adaptive meshing is used, and after doing the meshing, after completing the meshing part, what will go through is like we will define the solver. What type of problem is this? Like I'm dealing with some small design. I'm designing some antenna and other things. So what we'll do is we will use the HFSS FEM solver. These are the various solvers. So if we are dealing with some small design and other things, we will go to the FEM solver. When we move to the like, there is a much big design in comparison to like I can't solve that design with the FEM solver. So what we will do is we will use integral equation solver. So for bigger designs, we will use the integral equation solver. And when we move to the like big designs, like when we move to the not as when light phenomena comes into our like reflection and other things, when we come into the our scenario, so what we will use the SBR plus shooting and bouncing rays. So this will analyze like I'm placing some antenna over I'm placing an antenna over a car. Okay. So what happens is like there is a reflection and other things which comes with the phenomena. So for that purpose, we will use the SBR solver. And when there is a much big designs, like we can't solve whole design in one part. So what we will do is we will distribute that design in various cells, like unit cells. We will divide that design in the various parts, and we will do the simulations. This process is called domain decomposition method. So after solving, what we will do is we will move to the post-processing part. Basically, post-processing is divided into two parts. Like I want to analyze the field and I want to analyze the graph results and field results. These are the both different parts. Like I want to plot an electric field, or you can say that I want to plot some current density and other things. So we will do that from the field overlays, and like I want to plot some gain versus frequency plot, or as parameter return loss. You can say that. So for that purpose, we will use the result report. There's optimization, as already told you that there is a OptiSlang tool, but in ADT, like electronics desktop. So optimization is already inbuilt there. Like if you want to do the optimization, you can do from here also. So after doing that, we will use the multiphysics. Like I already told about flow simulation parts. Like I have designed something and I want to link that design to the circuit, or I am designing some PCB, and after designing, I want to do the near field analysis. So we can't do near field analysis in SI, so we will move to the circuit. So these type of things are called multiphysics things. Like I got some problem, so I can't solve whole problem with just one physics. So to analyze each problem, we need a different type of physics solutions. So this whole is called multi-physics domain. There's Ansys customization tool. Like I'm getting some problems and like I'm getting some issues regarding so Ansys customization tool will help you in that. So what we have done is first we created the geometry, then we move to the meshing parts, then we do the solvers from the different solvers. we solve our problem. Then we move to the post-processing part, done the optimizations according to our requirement. Like I want to link that design to the, like I'm designing something in the HFSS and I want to go to the circuit, or I want to do analysis in other things. So for that purpose, we will use the multiphysics. And if you are getting any problems or other things, we have a customization suite there. So what happens, like when I'm doing something, what I need is like I want everything at one place. I don't need to go like I am designing something, then I will go to the next one. I will go to the next tool and other things. So you can already couple whole design in just one phase. Like I'm designing some PCB and I want to do some thermal analysis. So what I will do is like just import, just click on the iStack part in the itself in the SI wave, and whole design will be imported to the iStack. So we don't need to go to the iStack like I'm designing some filter. I have in NU Hertz, what I have done, I have given the whole values, and like I'm designing some low pass filter. Okay, so I have just given the whole values, and after clicking export, whole design will be exported to the HFSS. So this was our technical, like how our whole tool work. So now we move to the HFSS part. Like I will explain each of our tools in details about that. So in HFSS itself, we are using three basic interfaces. We have a 3D modeler, 3D model, 3D modeler like basic HFSS. So I'm designing some antennas or waveguides, or I'm analysis of filters. Okay. So for that purpose, we have 3D modeler. When analyzing some PCB, okay. So like I want to analyze some PCB or go to the some ECAD designing part. Okay, ECAD designing is like IC connectors, wires, this type of thing. So what we will do is we will move to the 3D layout, and in the there is a linear circuit in which like for basic I'm designing some EMI, I'm doing some EMIMC simulations, or like doing some basic level of, and I want to couple our antenna into, I want to analyze in circuit. So what I will do is I will import that design 3D, the antenna design, the 3D modeler to our circuit. And in circuit, what we will do is we will connect the whole, like I want to connect some load, or I want to connect some resistor and other things. We will do that in the linear circuits. Those are the various applications where we can use our HFSS, like in the antennas, waveguides. I already explained you in the when I was explaining the 3D modeler. So next one is SI wave. So SI wave basically uses the hybrid solver. Like it uses some FEM and method of movement combined. So I'm doing some. I want to work on like I want to do some signal integrity, power integrity, or EMI/EMC. I want to do some DDR analysis. So for that purpose, what we will do is we will analyze that in the SI wave. In like as already everyone knows, like PCB is basically of different layers. To analyze each layers, we can do that in the SI wave itself. Like I have some IC packages. I want to inbuild that in the our PCB and analyze that. So for everything, we can solve in the SI wave. These are the various applications where you can use the SI wave, like for signal integrity calculations, power delivery characterizations, EMI, like I want to do some DDR analysis and other things. So we can do that in the SI wave. Q3D is basically, I already explained you that when we are extracting some RLDC parameters, like I want to design something. Okay. So what requirements we have? Like I want to work, I'm working on some PCB. Okay. So what happens? We need RLDC parameters. So to extract those RLDC parameters, we need a tool, which is Q3D and 2D extractor. When we are dealing with the 3D design, we will go to the Q3D, and when we are dealing with the 2D design, we will go to the 2D. Like I have some cables, wires, transmission lines to analyze that, to extract this RLDC. From this, we can use that to 3D and 2D extractors. It basically uses a finite element solver, and we can do DC and AC solver analysis both in the Q3D. So now I'm not. This is emit tool. Emit tool is basically like when we are like there is a traffic control. Okay, so in traffic control, I need to explore the things like how other things are affected. Like there is a some there's some vehicles coming and other things to analyze exact analysis and other things. We will do the Ansys. We will do that in the Ansys emit tool. These are the various applications where we can use the emit tools. Like we can use that in the RF system designs. Like I want to do some wireless and coexistence. I want to analyze like there is some interference in between the our analysis. So to analyze that also we can do that in the Ansys emit tool. So now this Ansys IcePack from like when we are doing some analysis. So temperature can affect from the chip level to the supercomputer level itself. So to analyze whole things, what we need a tool which can solve our whole problem. Like I want to some analyze some airflow. I want to analyze like there is a PCB and excess amount of current is we are receiving on that PCB, so it can burn. To analyze whole things and the temperature analysis, we will do that in the ice pack itself. So ice pack is basically like it is part of electronics also, but it uses FVM solver, which is CFD field. EMA, there is a EMA 3D cable. So like there is a cable already explained in the first slide. Like there is a cable installed in a car. So to analyze how the radiated coupling, radiated emission, and other things are dying, like just I will explain the example. Like there is an antenna installed. Okay, so the performance of the antenna can affect that cable. Like there can be an interference. To analyze that interference and other things, we will do that from the EMA 3D cable. EMA, there's a EMA 3D charge. Like for the charging and discharging phenomena, we are using EMA 3D charge. Like when we are doing the HV systems, the ECD ones, like in the PCBs and lightning attachment modeling, like these all things can be done from the EMA 3D charge. There's a new Hertz filter. I will explain you that this is a template-based tool. Here you can see that like I want to design some passive filters. So what we will do is we will just give the values and whole thing will be designed itself in the NU Hertz and it will be exported to the HFSS. I have to design some distributed filter or active filters, switch capacitors, digital circuit, Z match, everything can analyze from the NU Hertz filter, NU Hertz filter solution itself. So now when we are designing some antenna type of thing, like so during the design, what problem we face is like how to decide the parameters, like how height, substrate height, what substrate height I should take, what materials would be fit, if we are using like I am using some FR4 epoxy, okay, or using some derived materials. So at some particular frequency, what parameters should be used to analyze? We have Ansys antenna toolkits. What you have to do is here you can see that go to the HFSS antenna toolkit and which type of antenna you are designing. You can just go to that. Like I'm designing some rectangular patch antenna. Okay, so I will go to the rectangular patch antenna, and what I will do is like I will just provide the frequency and what type of material we are using. Okay, so after providing that, we will just click on the synthesis part, and after clicking on that, whole parameter will be what ideal parameters you should use. Those will be appear in that. There we have component library as one of also us there. Like I want to export some aeroplane and some like I want to export some human body. Okay, so these are the in the component in component library itself. These are the various 3D components inbuilt there, and you can import it from there also. These are the various examples which we have done in our tools. Like I have done some signal integrity and power integrity tests. Like basically, signal integrity is nothing like there is a receiver and there is a transmitter. Okay, so transmitter transmit the signal and receiver receive it. So what happens in between, how much losses and other things are done. So this will be analyzed from the signal integrity. And power integrity is basically like our device is capable of some limited power. So if we exceed that power, so it will burn. To analyze that, we will do that the power integrity test. There is an autonomy like I want to analyze some in the MA tools. I will explain you that some navigation techniques and other things like I want to do some traffic control systems. So we have done that here. Like I have designed one filter from the NURTS filter. So here you can see that this one filter is designed from the NURTS. There is an RF co-side, like there is an aeroplane. Okay, so the performance, there are the various components inbuilt in itself for the our aeroplane. Like there are the various antennas. So one performance of one antenna and the addition of one antenna can affect the other antenna. To analyze that, we have done the RF side in an aeroplane. There's a smartphone biocompatibility. Like I will just tell you that like when we are moving from one place to another place. Okay, so what happens is when we cross the line, so there is a network change. So to analyze that, we have a smartphone biocompatibility. Like here, LED here, I was talking with the antenna placement. Like I want to place some antenna over a car. To analyze that, we have done the antenna placement part. So this one was the introduction part. So if you have any query in the introduction part, you can ask. Yeah, you can import that design, Ashok. You can import any designs from the any software. Like you have designed some PCB in the LTM, okay, or CAD. You can import that design in SI Web itself. So if anyone else, any query?
Hi, this is Balaji here. I have a question. So
Okay.
the thing is, in SL Wave, let's say, you have a
Yeah.
PCB track and you have PCB layers, right?
Yeah.
So, and let's say I have a circuit simulation which simulates the current and voltage at every point in the circuit track. So how can I first import the voltage profile at each of the
Yeah, yeah. You
PCB
can like
track? Uh,
yeah, you can import that in the PCB track. Like I'm some you are talking about the voltage and current and other things. So what
yeah,
happens
so
like
let's say it's a time dependent simulation. Can I
yeah,
import the voltage versus time on the respective tracks and analyze the fields?
basically what happens is like first we will analyze the whole PCB and then we will move to the like I already told you about the co-simulation part. When we move to the Ansys a circuit part, you can import you are telling the voltage analysis and other things. You can import there also.
Okay, thank you.
I will move to the PCB analysis with ADT. This will focus basically on the 3D layout. And so what we'll do is we will now move to the PCB analysis part. So in today's time, like when we are dealing with some simulation and other things, what basically drives like electronics reality, like there is a lot of new features increasing. Like when we want to do some improving the first pass yield, like I'm designing something and I'm facing some problems in the like avionics or other consumer electronics parts. So this whole part is like electronics is not a market, but electronics is basically part of every market, as you already know about that. So these things can be done to like I want to some lowering some PUM cost and other things. So these things can done from the electronics reliability. So what happens is like in the when we are you are not doing the simulation, what you do is like I design, then I build that design. I have just like I've taken some parameters. I do some designing part, build some analysis, and then test. Then we came to know that there's a fault detected. So what we need to do is like we will move to the designing part again. Like till the problem is solved, you have to repeat this process continuously. So what simulation do is like the simulation what will in the designing itself. Yes. Before designing our design, what we will do is we will analyze what type of problems we can face after the designing. So this thing can be done from the simulation part, and then we will design and do our testing. Then the error section will be removed itself in the simulation part. Like what are the basic requirements? Like I when I'm doing some analysis, so what we need is like we want to increase the performance, safety part, and we want to minimize the cost. When you are dealing with the other phase, like for each testing, you need uh, you have to pay. So to reduce that, like if you are doing some five testing and other things, if you can reduce that five into just one, so cost will be automatically decreased, performance will be automatically increased, and safety analysis will be our increased. So doing the electronic reliability, what do is like it makes us faster. It makes us like we are compatible with the market. Like what happens when you got some problem, the customer will not wait. They will tell that like I need that in as fast as possible. So we will if you can't deliver that, they will move to the next one. So for that we can improve the timing and reduce the cost also. So these are the basic our when we are dealing with the PCB. So these are the basic reliability tests we needed. Like I want to do some electrical reliability, thermal reliability, mechanical, comprehensive multi-physics, physics analysis. So all things can be done from the Ansys itself. So now when we are already talking about the electronic reliability, about electronic reliability. So what are the four basic things which will be included in the electronic reliability? So these are the signal integrity, power integrity, thermal integrity, and electromagnetic interference and compatibility. Signal integrity is basically like I'm delivering some network like 101 from the transmitter and receiver received the 101. So the signal integrity loss is there. There is no loss in the signal itself. So this all things can be done from the signal integrity analysis. Power integrity analysis is like I want some. There is our PCB. It is capable of some limited power, but we are exceeding that power, so it will burn. So that is done from the power integrity test. Thermal integrity, as I already told you about that, like I'm working on something and there is a temperature based temperature is affecting that design. So that part is thermal integrity. Electromagnetic interference is like I will just tell you with one example. I'm watching TV. Okay, so there is and a mobile is placed just below the TV. There is when call comes, there is interference in the signals. So this is electromagnetic interference. And compatibility is like how compatible our device is to receive all type of signals. Like I want to do the simulations, but I want to know that how compatible our device is to receive all type of signals. So as I already explained you that this one is like I'm doing some signal integrity test, and I want there's a one streams of bits, ones and zeros. So like here you can see that 10 1001100001. This signal is transmitted, and at the receiver end, what type of input output we are getting. To analyze that, we will do that. We are doing the signal integrity test, and this is our eye diagram. Eye diagram basically works like uh, when we close our eyes. Okay, so the wider the eye, our eye is open, the more accurate I will know that how visible other things are. So here also, here you can see that this part acts like an eye. So the wider this will open, the more the radiation will be done here. Power integrity is basically like how I already explained you that how how much power it can take, and above that power if we are giving it, so there will be the burn and other things. To analyze that, we will do the power integrity test. These things will be done in the SI wave itself. So now we will move to the EMI part. EMI basically deals like I'm working EMI basically in every field. Like I have some I'm doing some performance of antennas. Like in the examples field, I will explain about that the foresight field. There is a multiple antennas inbuilt there. So the performance of one antenna can be affected from the interference of other antenna. Okay. To analyze whole thing, we will do that electromagnetic interference. And electromagnetic compatibility will be basically like how compatible, how like when we know how compatible devices, so we can accurately give signals and other things. So now I will, before moving to the case study, first I will let you know that if there's any query till now or not. Everyone, Rahul, Mansu, you have any query? Everyone, please make this webinar as an interactive. Just ask questions. Like if you have any questions, you can ask. If you are if you want to analyze, do some other type of problems you have, you can ask here also. I will let you know that about the. If I don't know that, so I will come to you. But please make this session interactive. So let's move to the case studies. So in EMINC itself, there are the various tests we can do. The first one here is you can see that this is a conducted emission test. Okay, so there is an LISN, there is an UT. So how that our equipment under test working in presence of these virtual grounds and LISN. So we'll analyze in the conducted emission test. So what we'll do is we will import the board. What we'll do is we will import the board. We will extract our RHGC parameters and other things. We will do the system simulations and what type of how noises are affecting our design and other things. We will do that. And if there is any error on other things, we will again move to the system simulation part. Next one is radiated emission test. So in radiated emission test, what happens is like in there is a UT and there is an antenna placed over some distance. Okay, like 3 to 10 meter distance, there is an antenna placed. So to analyze how our UT is working in presence of that antenna, how those performance of the antenna affecting our EOT. This will be done through the radiated emission test. Radiated emission basically is like far field analysis. Like everyone knows about the far field analysis. So the far field analysis is basically like radiated emissions. There's a one of our customer, Gamco. They provided like there is an antenna placed over some 3 meter distance. Okay, so to they told us how this our spectrum analysis will be done. So they have given the measurement value and we have simulated. So here you can see that the accuracy level approx uh, our simulated result is matching the measurement result. So this tells about our accuracy. So now we will move to the SI wave part. I already explained about that. SI wave is basically for signal integrity and power integrity analysis. So in SI wave extraction capabilities itself, we can do the DC analysis, AC analysis, resonant mode. We can one of you asked like how we can import the design also or not. So we can import any designs. We want to I want to work on the spice. We have some spice models of some other things like we have some capacity and other things. We have a spice model of that. We can import that itself in the our design. We want to run some I square drop test, and we want to run some DDR analysis or signal flow graph. So whole thing can be done in the SI wave itself. And here you can see that these are the some of where you can import the design PCB like mental graphics, LTMs, you can ODB plus, Ansys EDB. So you can import whole design here. So this is basically a workflow wizard, how our SI wave works. Okay, so there you can see that when you open the SI wave, first thing will become like import component file. Okay, then stack up import, verify stack up. Then we will move to the verify port stacks, where we move to the circuit element parameters. Port stack is basically like arrangement of the whole our other components. Verify the power and ground nets, sanitize our layout, assign S parameters, and they think like here you can see that these parts are compulsory parts. This you have to done, and this thing can be according to your requirement. And after importing or analysis the whole design, you can compute the DCIR, compute the EMF test, SYZ parameters, resonant modes, frequency, far field, near field, and you can do the signal net analyzer. There is an SI wizard testing. Like I am working on some DDR analysis. Like I have some DDR3 or I want to extract results. So we have DDR wizards, DDR wizards. So this whole tells about that our workflow and what how our tools look like. These are the various features highlights for that. Like I want to speed up our simulations with the HPC. We can do that. I want to some I want to do some layout scan capabilities, which is more accurate than cadence. I want to do some signal environment testing. Like I want to unlike where you have seven unlike security where you have seven executed. Security is basically our competitor. We can do the power delivery network AC flow. We can do the CPS based workflows and other things. We can do the PCIR and thermal PCIR plus thermal testing, which is basically more accurate than the cadence and completely automated workflow we have. So these are the basic part where you can analyze that how we are different from our customer and how SI wave is more accurate and more uh, easy to work with than other tools. So next one is like when we are dealing with the PCB, we already told about when we are dealing with not only PCB but any AP design. So for that we have HFSS 3D layout. So in HFSS 3D layout, we have different type of things like I want to some in the SI web itself, you can also analyze the stack up and other things. But in 3D layout, you can do that. I want to create some ports and other things. We can do that. We can import some designs. I want to some electrical CAD designs and other things. Like I have some stack up wires and wire bonds, so we can do that in the HFSS 3D layout itself. This is a GUI for the Ansys HFSS 3D layout. Like here you can see that when we open the design, these things will become like there will be the HFSS, Q3D, circuit, IcePack, Maxwell's, Implorer. Everything will be in the ADT itself. And when you click to the HFSS, you will come to know that there is a HFSS, which is a 3D modeler, and there is an HFSS 3D layout, which is basically for the PCB analysis and our other ECAD design analysis. So either you have to choose the like what type of some solution type you are using. Like I want to do some model testing or eigen mode. We want to go to the eigen mode characteristics, or I want to do some transient analysis. I want to move to the SBR plus. So you can choose according to your which solution you want to use. These are the basically when we are dealing with the full PCB assembly, we can do that in that. It contains geometry, material properties, excitations, design parameters, and everything. So these are the various workflows where we can do that. So like I'm doing some signal integrity analysis workflow. Okay. So I'm doing some signal integrity test. So what we will do is first we will import the ECAD design. Like here you can see that you want to import from any type of like I'm working from the AutoCAD or LTM and other things. You can import the design here. Then extract X parameter from the like our tool. Then build the circuit model. Okay. After doing the S parameter, we will move to the circuit part. We will import the geometry in SI wave PCB geometry in the circuit, and we will analyze that. We will do the transient response. Like when we are doing some testing, like I will do some transient analysis, and I will move to the analyze the results. Like I want to there you can see that there's an eye diagram test here. So this one was the for the signal integrity analysis. When I want to do some conducted emission or rejected emission test. Okay. So what we will do is this is basically like first we need to the import the PCB file in SI wave. Then we move to the S parameter assignment. Like I want to some assign some spice models and other things. We'll do that. We will create the port itself in the SI wave. We will do the SYZ simulations. We will import solved PCB blocks in the circuit. This phase, this one, here you can see that this will be done in the SI wave. Okay, this will be done in the SI wave from PCB file import to SYZ simulations. Now we will move to the circuit, ADT circuit, and we will import the PCB blocks in the circuit. We will import the active and passive components spice model. Like I have some I want to import the spice model of capacitor or IGS model of a transformer. Another thing we will import that. We will make the whole connection for we will make the whole connection. We will do the transient analysis, and for the conducted emission we are doing transient analysis. After doing the transient analysis, we will push excite our design to the SI wave. We will do the excitation, and we will move to the SI wave. And you don't need to change anything in the SI wave. All design the after doing the push excitation, our whole changes which we have done in the circuit will be applied to the our PCB. So we will go to the again SI wave. We will plot the Parquet analysis, which will be the radiated emission plots. So this is basically the workflow for the our PCB level conducted emission, radiated emission test. So this one was for like we had done our EMI part. So if you have any query, you can ask here. So
Yes,
first
yes.
step, first step we need to do is like we will open Ansys SI wave. Here you can see that. I click on here. These are the four tools. This is ADT where you will get HFSS and other things. This is SI wave. I explain that later. So first step is we will import the design. We will import our PCB. So here you can see that we will click on the open project. There's a so here's a four-phase buck circuit. We will click on that. We will open it. Clicking on Control D. Clicking on Control D will fit our design. Fit full of PCB here. This is our whole design. Here you can see that. To this. This is import the component file, import the stack up. I already found out, verify the stack up, verify port stacks, verify circuit elements, power and ground nets, sanitize the whole design. So now what we will do is we will first validate our design. Go to the validation chat and in validation we will select the simulation mode to be the XYZ parameter. We'll click all these points and force we will use the core force. According to you, according to your requirement, you can choose the course, how much core you want to use. I've selected the 4 core, click OK. Here you can see that there is a no error, but if there's some error, here you can see that there is an auto fix button. So if there's any error, we can click on the auto fix and our that error will be resolved. Okay. Now we will assign our ground and power nets. Here you can see that these are the some ground and power nets. So if any ground and power nets is above or below, so what we will do is we will click on that and we will just click down or up button. Like if we are going from the like I want to dedicate to the non-power ground nets. So what I will do is just click on this up button and our this ground and power nets will be go to the non-power and non-power nets. Okay. So next step will be like I will assign pin groups for that. So in the I will go to the components, going to the components and click on input and output. Input and output. Just click APC and we will choose this part, this pin. And what we will do is here you can see that the tools, create and manage. Go to the tools and create and manage pin groups. Click here. In the reference designator, you have to choose J1 and in the next, in the ground and P12. So after that, what I will do is we will create a new pin group create on the new pin group, and here you can see that a pin group is created here. Just close it, and now we will move to the port assignment. Like I will assign the port, Control D here. Now we will move to the port assignment. Just here you can see that port assignment is basically we can do in two types. First one is manually, and second one is automatic. Okay, so I will just first go to the automatic part. Generate circuit element on the component. Click here. Click J1 in the P1 group. In the positive terminal, click P12, and in the reference terminal, click ground. Okay, here you can see that there is a port, and click create. And when our whole design is on the our reference, so we will choose 0.1 ohm. When our non-power power and ground nets are using in the on the reference plane, so we will go to the 0.1 ohm. And if there is use on non-power non-ground nets we are doing, we will move to the 50 ohms. Click OK, and code will be created. So I have to repeat this process for Q1 also. So what I will do is click on the Q1, P12, same process, go to the ground, click on the create, OK, oh, done. And this by this we can create a port. Okay. Now I will tell you that how we can create port manually. Just click here. Showing that is okay. So go to the home. After going to the home, here you can see that these are the various. I want to like add some capacitors. I want to add some inductor or resistor. So in this, you can see that add a port. Click on the add port. First, click on this point, then move that in the other phase. Click there, and here you can see that after creating the port, like what top layers it is taking, top layer ground, the ground layer in the power net which one is P12. So click OK, and again here you have to put 0.10. Click OK, and you can see that a port is created here. Okay, so this by this we can by these two methods we can create the our ports. So now I will generate our SYZ parameters. So we will move to the simulation part, and here you can see that compute SYZ parameters. Click here, give the values like 1 hertz to 0 to 1 hertz. Yes. So then we will move next. So in the frequency sweeps, we will give the in the first sweep will be a 0 to 1, and we will use the linear distributions. And from 1 hertz to 1 megahertz, we will use the bi-decade distributions. From 1 megahertz to 1 gigahertz, again we will use a linear step. Click on the launch button. Okay, clicking on the launch button here, full our SYZ parameter will be created here. Okay, just click here, double click. This is our SYZ parameters. Clicking here. Okay. Sorry, just a second. Like I want to analyze all our things. So I will take this, and here our SYZ parameters will be included. And like if I want to view that in details, I will export that in the Data Explorer. Click here on the Data Explorer, export to Network Data Explorer. It will just take a few seconds. Yeah, you can see that. In this, you can view any type of business. Like from less parameters, I want to view return loss. I will go to the return loss and analyze from each layers. Here, I can do add for the like I want to analyze for the Y parameters or Z parameters. Okay, so I can do that. Like I want to do some port impedance testing. Like I want to do some gamma testings, other things. So we can do that from the exporting that to the Data Explorer, and like I want to plot that in the ADT itself in the HFSS. We can do that in also. We just click on the plot in electronics desktop, and whole design will be moved to the electronic desktop. Okay. So one thing I was explaining you that if I want to do the thermal integrity test. Okay. So here there is an option ice pack. When I will do the transient testing and thermal analysis, just whole design will be imported to the ice pack itself just by clicking here. Now I will go to the electronics desktop for the circuit analysis. I will open ADT. Now after opening ADT here, you can see that I will explain you that these are the various tools. This is HFSS, Q3D, Circuit, Emit, IcePack, Maxwell, Simplorer, Mechanical. There you can do the MCAD simulations in the mechanical itself. So first I will do open, go to the open. So here you can see that there is a bulk circuit. I will open that file. I will save it here again. Since that was a zip file, I need to save it whenever I'm doing simulations. So here one of the our sub-circuit is included here. Just click here and click Control D, and here you can see that our whole design is imported here, like a whole circuit for the our conducted emission test is here. These are various sub-circuits included, switching circuits. This is our analysis part where we are using LISN and the voltage source. This is our SI wave link. Now, next, what we need to do is we have to import our spice model for capacitor. Go to the symbol part. After going to the symbol, click on the models and In the models, click on the PSpice, and here you can see that there is an spice model for that, and click open. After clicking on open, I need to give it a symbol of capacitor. So what I will do is just click on the symbol, type here cap V. Okay, click OK. So click OK, and here you can see that this our capacitor is imported. Click here and this. By clicking on the escape, you will escape the drawing panel. Just click on the capacitor, and by clicking Control R, so our capacitor will be rotated. Again, click here, Control R. Here you can see that we have placed the capacitor. Now I need to place our SI wave design. Okay, so what we need to do is we click on the four-phase circuit, open that, click on the four-phase circuit, go to the add subcircuit. After clicking on the add subcircuit, click on the add SI wave link. Click add SI wave link. Click on the four-phase buck circuit. Click on the four-phase buck circuit. Click open. Here you can see that our SI wave dynamic link is here open. Click on the OK. We can close the SI wave design because we have already done the simulations here. So we close that. So now here you can see that our SI wave file is imported here with 31 pins. So I need to export it here. So first I will move little bit. I will click on this design, import that design here. I have imported the design here. So now if I want to see any particular design, okay, like I want to see that our subcircuit. Just first click on that and click here. Only first this, like I want to see this. So here you can see that in the properties window, you can see whole property of this component, like what route is using, what type of CDSN and RSLS it is using, everything. Click here, right click, and from the push down button, this whole switching circuit will be opened. Again, move to the our four-phase box circuit. Okay, so this is our LISN part. This is our input. This is our input. This is output. This is our input. This is output. Here is our SI wave design, and these are the four subcircuits we are using. So now we will move to the transient analysis. So after doing that, what we will do is we will go to the analysis. Click on the right click, add Nexum reports, transient analysis, click transient analysis, click from the one NS to 200 US. Okay, click OK. Now click right click, analyze. This analysis part will take 2 seconds. So this was the basic workflow for how we can do the PCB label simulations in our Ansys electronic desktop. Like from adding ports to doing the simulations and other things, we can do everything in the SI wave. And when we want to do the near field analysis, like I want to do the conducted emission test, so I will move to the Ansys electronic desktop. And after giving the Nexum solution data, Nexum transient analysis, I will analyze the result. So here, so for this phase from this 100 to 100, this linear phase, we will analyze our conducted emission result. So for that, what we will do is we will just right click on that. We will create standard reports, rectangular plot, and after clicking on the rectangular plot, this window will pop up. Time, the plotting range will be already inbuilt as we have given in the analysis. Our analysis, we will choose in the category voltage, V in upon V out, choose none, and just click on the new report, and this report will be generated. Same process we will do for the our AMI conducted emission test. Here you can see that click on the voltage, like go to the EMI REC port, and in the DBU you can select that. In units we will select the DBU, and we are doing in the spectral analysis. Okay, we want to view our result in spectral. So what we will do is we will start from the 100 US, stop at the 200, and maximum frequency will give to 100 megahertz. And click check on the plot continuous spectrum and real time. Click on the new report, and this report will be generated here. Like at the M1 point, when we are getting the spectrum at a 0.1, the voltage 103.741. So according to your requirement, you can go through that. This will be done from the conducted emission test. And like I want to change some parameters and other things, just double click here and go to the X scaling. Like I want to start from, like I'm starting from the 0.15 and ending from the 100. And you want to change that, you can change that here also. And doing that, now we will move to the edited emission part. For edited emission, what we will need to do is just click here, and as in the workflow, I have already explained you that in go to the push excitation. By clicking on the push excitation, our whole design will be import to the SI wave. Save that design, close. Now go to our SI wave design. Click here. And that was a conducted emission result. And when we move to the radiated emission, we move to the simulations, go to the simulations. And here you can generate the compute far field report. Compute far field report. If that as it is. Okay. Click on the launch. By clicking on the launch, our result will be generated here. So if you have any query, you can ask right now. This was complete workflow and one of the hands-on design for our PCB level RE and radiated emission and conducted emission test. Now, if you have any query, you can ask